Okay, good morning, everybody. So we continue our discussion on AI approaches to validation of cyber physical systems. If you remember, we do a quick recap. We started with two kinds of specifications, a logical specification and a behavioral specification. And the logical specification, we have discussed propositional temporal logic. And for behavioral specifications, we have discussed finite state machines. And there we said that even in a particular logical or behavioral specification, the specification will be refined at various levels. In order to understand logical specification, we discussed temporal logic, and there, in addition to the Boolean operators, we added four operators: G, F, X, and until, where G meant that globally. So we are working on infinite traces, which we have discussed. And GP means along the path from that state globally, the condition or the property P is true. FP means in future P is true. XP means in the next state P is true. And P until Q means either Q is true or P continues to remain true till Q becomes true. We also discussed this timing versions or timed versions of these operators. When we write G48P as is given here, then we mean that the property P is true on the trace between 4 to 8. So all steps from 4 to 8, it is true. FMNP means that the property P holds somewhere between M and N. It may hold everywhere, but at least it holds in one of the points. XMP means it holds at the mth step after now, and P until Mn Q is that the transition occurs at that time. And we went through our sprinkler example. And for our sprinkler example, that is our running example, we defined 6 Boolean variables. We had two of our operators, we had two sensors, SA and SB, SA for the field A, SB for the field B, and we defined 6 Boolean functions: dry A if it is less than the desired point, dry B if B is less than the desired point, nor A if it is within the range, and wet A if it crosses the range. These are the soil sensors. And at level 0, we wrote two untimed operators. It says globally, not normal A implies in future normal A. Second is globally, not normal B implies in future normal B. We also wrote some timed operators. We said here, globally dry A implies in future between 0 to 3 time steps, it will become normal. Dry B means between 0 to 4 time steps in the future, it will become normal. Wet A implies 0 to 5 time steps, it will return to normal, and wet B 0 to 7 time steps. This was level 0, and here in this level 0 specification, there were no sprinklers. Then we moved on to two sprinkler definition at level 1. So we went to our first refinement of level 1, and we added two more Boolean variables, PA and PB. PA to signify that sprinkler A is on, PB to signify sprinkler B is on. And now with these two more Boolean variables, we started writing properties including the sprinklers. And we said that dry A, globally dry A implies in the next state, PA is true till, that means sprinkler A is on until it becomes normal. Similarly, if it is dry, sprinkler B is on until it becomes normal. If it is wet, sprinkler A is off until it becomes normal. If field B is wet, then sprinkler B is off until it becomes normal. We also wrote down the state machines for the sprinklers. For example, for sprinkler A, we wrote down that it is in state off, and if it is dry, it becomes on, and it remains at on if it is normal or dry, and if it is wet, then it again becomes off. Similarly, you can write the sprinkler for B. And we discussed in details the following things. The first we said, and we'll come to that a little later. Then we also said that if we have a similar sprinkler definition for B, then the composition of A and B, which is the global state machine of the two independent sprinklers, will have four states. One is whether P is off, B is off, then P is off, B is on. A is off, B is off, A is off, B is on, A is on, B is off, and both are on. And that can be formed by the composite. So this gives us the global picture. And here we were interested in several things. The first thing we were interested is whether the defined specification meets whatever is the original level 0 specification. That was our problem, and we'll come to that a little more again. We also wanted to see whether the logical specification and the finite state specification have got compatibility. Now here we have discussed something very interesting last day, and I want to know if anybody remembers that the finite state machine that we have defined for sprinkler A, working of sprinkler A, it has some case which is not defined in the logical specification, but it does not violate the logical specification. Can anybody tell me? Does anybody remember which part of sprinkler A behavior is not specified in the logical definition?
And what to do in normal A? Normal.
Right. Very good. State machine, then you will see that this case and this case talk about what happens when it is in normal state. So in the normal state, if it is off and it is normal state, then the finite state machine keeps it at off. If it is on and in normal state, the finite state machine keeps it at on. That is a decision that has been taken, but it does not violate the condition that is given in the logical specification. Is that clear to everybody? That was a very important point. Yes, about sir. What? Yes. Then we went to the three sprinkler definition, where we wanted to have a third sprinkler, which will ensure that whenever both are wet, then the third sprinkler will be on. So we rewrote for the third sprinkler, saying the rule is G, dry A and dry B means the third sprinkler is on so long as until either one of them become normal. We also said that if both are not dry, that means both of them are not dry, that means one of them is at least normal, then the third sprinkler is off. And if the third sprinkler is on, then the first two sprinklers are off. So this is how we wrote this, and we said that now if I have a state machine for a sprinkler, then again we will end up with a 8 state machine, and if we have one for the controller, then we will end up with 16 state machines. So with this recap, we discussed what is our verification problem. We have specification at 3 levels in this case. No sprinkler, 2 sprinklers, 3 sprinklers, which are the rows, and we have a temporal specification and a finite state specification. We did not have a finite state model here, but we had a finite state model in the other 2 levels because those were refined where the sprinklers property was given. Then we talked about a verification between levels of the same category, which we called as intent verification. And we talked about specification versus behavior checking, which we talked about as implementation verification, which we will implement by a method called model checking. And there are several other issues. So with this as our gamut, we discussed various other things. So with this as our gamut, we will do one more example today so that we are sure about what we are trying to do. And then we will move on to other aspects. So our problem is as follows. There is a box which receives requests R1 and R2 and gives grants G1 and G2. So there are 2 request lines and there are 2 grant lines. The system requires to arbitrate between request R1 and R2 and provide grants G1 and G2 in such a way that R2 is default, but R1 is given higher priority over R2 and mutual exclusion must be guaranteed. If this is the specification in English language, so how do we write the rules? We write the rules in the following way. If we say globally, if R1 is true, then in the next cycle, what should be true? If R1 is true in the next cycle, what should be true?
G1.
G1 should be true. So this is what we have written. And if R2 is true, what should be true in the next cycle?
G2.
But how will you say if I write down globally R1 implies X G1 and I write down globally R2 implies X G2, how do I write mutual exclusion? Both cannot be true together, isn't it? Not of G1 and G2, both cannot be true together. All right. Is that clear to everybody? If I write down this specification, can anybody tell me something about this specification?
Sir, R1 has the higher priority, so that is not there.
No, but if somebody wrote down this specification, then what analysis could you do about this specification? Is this specification consistent? Can anybody tell me whether this specification is consistent or not? Suppose R1 and R2 come at the same time. Then will the specification be violated?
Yes, the specification will be violated.
Yes. So this specification will be violated if R1 and R2, sorry, come simultaneously. So consistency checking or self-check is an important formal check. So if you write down a specification, the automated method can do a formal check. So if this was L0, then this L0 is inconsistent. Is it clear to everybody?
Sir, from these three specifications, can we derive that R1 and R2 can't be on at the same time?
So R1 and R2, yes, obviously you will derive R1 and R2 cannot be on at the same time. No, you cannot. R1 and R2 is not under your control. So,
okay, sir. Yeah.
so that is why we write a refined L0, or let us call it an L0 dash specification. And in the L0 dash specification, what change we have made? This is L0 dashed. First one is the same. Second one we have changed. If R2 is true and R1 is not true, and then in the next cycle G2 is true. So this, even if R1 and R2 now come simultaneously, which one will be on in this new specification? L0 dash G1. And it satisfies this condition.
Yes, it's consistent.
It is consistent and satisfies this condition. But my question is L0 dashed complete? That is another part of the self-check. Is it complete?
No, sir, because it doesn't handle the case where R1 is 0 and R2 is also 0.
Right. Does not handle case when both are 0. So completeness checking also on the specification is an important check. So in order to do that, we now write the L1 spec when we add exactly what you mentioned. And when we add that part, then we add this rule. We said that by default, where is the grant? By this rule, the rest of the rules are same. We have added the fourth rule. What does this say? That if none of them are requesting, then the grant is, which line is high?
G2.
G2. Now, we know that L0 was originally inconsistent, so it cannot be used. It was refined to L0 dashed. So now, which was consistent but not complete. Now we have made L0 dashed. Now we want to check whether this does L0 dashed. If I refine it to this, does it violate anything in L1 dashed? In L0 dashed? No. That means I had my L0 dashed and I have refined it to make L1, but L1 does not violate L0. So this is the intent verification step. Yes, please.
So instead of like adding this fourth step, we can modify the second step, right? We can remove the condition that R2 is true. We have to just check that if R1 is not true.
Correct. You are right. The other way you could have written was you could have just written if not R1 implies XG2. Aditya, you are absolutely right. You would have combined these two and you wanted to write, instead of these two, you wanted to write globally, not R1 implies XG2. Correct?
Yes, sir.
But what? So this, if R1 is not true, then in the next cycle. So that is also, now you can see, suppose this is my L3. Now L3 and L1 are equivalent. You know, you studied equivalence in normal Boolean logic. So here in temporal logic, you also can show equivalence. Correct? Very good. Anybody else has a point? Now, suppose I implement it by hardware. And eventually I will implement it by hardware. This is the hardware or an implementation which defines a behavior of the system. Can you tell me, does the behavior of this system here, does it satisfy my temporal specifications? This is a delay gate. This is a delay gate. This is an AND gate, and this is a NOT gate, and this is the delay gate. And this is just a buffer. This is just a buffer delay, one unit delay. So does this implementation meet the specification? Are all the conditions satisfied?
Yes, sir.
Sure. Take the case when R1 and R2 are both 0.
Then no, sir, it will both be 0. G1 and G2 will be 0.
Correct. So which one is violated? This one is violated by the implementation. So I will do a check. So this is part of implementation verification and model checking. And somebody gives me the hardware implementation and gives me these temporal formulae, I should be able to check whether it is satisfied or not. Clear, everybody? Anybody has a question? Can you see how it is violated? Now
Yes, sir.
I need not have implemented in hardware. I will write, say, a C program, which is a behavioral program. So I'm giving you an equivalent of a program. This is written in a hardware description language called Verilog. And it says that always at the positive edge of the clock, always means this is an infinite loop from that beginning to the end at the always block. It says if R1 equal to 1 at the positive edge of the clock, do G1 1 and G2 0. If R1 is 1 and R2 is 1 at the next clock, make G2 1 and G1 0. If R1 is 0 and R2 is 0, at the next cycle make G2 1 and G1 0. So this is a behavioral code. This is a code. This code can be converted to a finite state machine. Like the way we wanted to do our finite state machine, So there are automatic methods to take code and convert it to a finite state machine. And then if you check the model on the finite state machine or on the code, then again you can check, or you can do a model checking to check that this implementation correctly implement the specification. So based on this, you can go through all these steps that we just mentioned here and we discussed in the last day about multiple level specifications, and then move on from multiple level specifications. I'm not sure if my screen is coming to you all. Has it come?
Sir, it's in. Now it's come, sir.
Yeah, now it has come. So this was the whole verification paradigm. That is in the same layers intent verification and across layers implementation verification. So let us just understand this. And while these are toy examples, here is a specification for a fuel controller of an automotive fuel controller. So it has got two boxes. One box is called the fuel rate controller and the other is called the engine gas dynamics controller. And there is a throttle command and every other thing. And this block can again be refined into mode blocks. So this is the fuel rate controller. So what I have done is I have got a specification with some input output, and then I have refined and created further blocks. So for example, my level I could be a architectural specification with four lines, input output lines. Level 2 will now have more detailed block diagram. So this was my block diagram B. Now this B is implemented by A1, A2, A3. So I will write temporal properties on X1, X2, X3 and X4 at this level for B. In addition, I will write temporal properties for A1, A2 and A3. A1 will be written with X1, Y4 and Y1. A2 will be written with X3, Y4, Y1 and Y2. And A3 will be written with X2, Y3, Y4, X4 and Y2. And the connection will be given. And I need to now check whether Li satisfies, Li plus 1 satisfies Li. So this is the more general form of intent verification. And in order to do that, all I will do is I will develop the temporal formula TLI plus 1. I will take A1, A2, A3, A4 and do the connection, and I will check whether all the TLI plus 1 implies TLI. So this is my intent verification problem. So this is the formal method, and if it does not, how do I find the gap? What is the gap? What is the intent gap? The intent gap can be determined by the formula of TLI plus 1 and not TLI. The formula TLI plus 1 and not TLI tells me that there is something that TLI plus 1 does, but TLI does not do. And if this is not null, then the refined specification does not properly implement the original specification. So if I had the original specification, then I added 2 sprinklers. I must check whether the 2 sprinkler definition implies the without sprinkler definition. I must check whether the 3 sprinkler definition satisfies the 2 sprinkler definition. And if it does not, then I can automatically find the gap by finding out the min terms, the equivalent temporal min terms of the formula TLI plus 1 and not TLI. So this is where the magic of formal methods comes, and you can automatically use the formal methods of AI to do your intent verification. Any questions? Have you understood? Just say yes or no. If you have not understood, I'll go back and tell you what it is all about. Can you hear me?
Yes.
Shall I proceed?
Yes.
In the implementation also, you have a similar situation. You will have a behavioral model. So you'll have a single state machine for this. Then this is for B. Then for A1, A2, and A3, you will have behavioral models. And you will have the connections. So you will create what is called the composite model from L1. This is L0, let us say. And now you will check whether the behavioral model BL1 satisfies BL0. This is the intent verification problem at the behavioral level. So these are 2 intent verification problems. Then the implementation verification problem is, what is the implementation verification problem? It is to check whether implementation verification will check TL0, BL0 implies TL0, or BL1 implies TL1. And this is implemented by model checking. We cannot go into the details of these, but all these are fantastic algorithms that you can develop. And if you all want, I can take another class later on to tell you what these algorithms are, which automatically does this sort of verification. In addition to this verification, there are several interesting things. We did that self-check a little while ago in the arbiter problem. Similar checks can be written in the sprinkler problem. Now, let us consider my property which says this. Whenever request R1 arrives, grant 1 must be given in the next cycle. And we had written it this way. Globally, R1 implies X G1. This is fine. But suppose somebody wrote it as this. What does this say? That if R1 is true, in the next cycle G1 is true, and what does the second term signify?
The next step, the G1 is not true.
Right. So it says that only and exactly for one cycle. Because he asked for this exactly in the next cycle. To implement exactly, he put it down, the specification, put it down. This property is satisfiable because if the request does not come, you don't have a problem. But this is inconsistent. Why is it inconsistent? Can anybody tell me?
Sir, if R1 is still still on in the next step.
Correct. That means R1 is on in step 1 as well as in step 2. Then, so if R1 is on, very good, at step 1 and 2, then the formula will require G1. One formula, one part will require G1 to be on at 2 and off at 3. The other, so R1 at 1 will require this, but R1 at 2 will require G1 to be on at 2, at 3. And therefore, so there are some very interesting nitty-gritties that can be done with the power of temporal logic. Any questions here? Are you following or not?
Yes, sir.
Yes, sir.
Yes, sir.
Good. The other problem that we discussed the last day was what is called the state explosion problem. And as I just told you, that if I use programming code, size about 1,000 or 1,000 states. FSM, 1,000 state FSM. And I will have 2,000 such pieces of code. You can imagine how much will an aeroplane code be, how much will the code of a autonomous vehicle be, etc. So the total number of states will explode to 2,000 to the power 1,000, isn't it? Or 1,000 to the power 2,000. What? What to the power what? If each state machine is 1,000 and there are 2,000 such machines, it will be
2,000, 1,000 raised to 2,000.
What is the largest number that you know which exists in real life? What is the largest physical number that you know which exists here in this universe? As you can imagine that this number is so large. Huh?
Order of 10 to the power 24.
Yes, Avogadro's number, right?
Yes,
6.2023 into 10 to the power 23 or something like that, right? And
yes,
isn't this much bigger than that? So obviously, if you want to practically implement these things, you won't even be able to store them in the memory. So there comes this very, very interesting challenge which came to solve the state explosion problem. And there were two approaches. One came from Randall Bryant, which developed a new data structure which implemented the present state, given the present state, next state table, as a binary decision diagram data structure. Very interesting. If required and if we get time, I will explain this to you. And by this, they were able to solve very, very large machines, very, very large problems. The other, they used logical reasoning and they opened it up. The temporal problem was opened up as a Boolean problem in time. So this was called bounded model checking. So they converted a temporal problem into time steps T1, T2, etc. and wrote this formulae, the Boolean formulae for each time step. And they opened it up for millions of steps, and they used the AI solvers to solve such problems. These cases for consistency, model checking, and everything else. And by this, in practice today, reasonable size systems are managed. There are other things also for which I don't have the time in this 1 hour slot. So the next, so if we look at functional verification, then we come back to our whole diagram of functional verification, which is this one. This is our architectural specification. Then we refined it into multiple levels. Then we created state machines. And finally, we create code. And we have intent verification and model checking, consistency checking, all of this to be done. But practical systems require other parameters. One of the other parameters that practical systems require is timing. So here is a specification of a airbag crash scenario. So it says the high level specification L0 tells me that if it is a crash, then the airbags must blow. The L1 functional specification says that disable the power steering, collapse the steering, and then blow the airbags. Now, if this is the functional specification, then there will be an added timing specification to this. And when you do from L0, timed L0 to timed L0 to timed L1, then you will end up with trying to find out values of X, Y, and Z which satisfy this constraint. And that is what I had very subtly written down in the example of the car controller that I had shown in the last day's class. Let me come back and show that. This one. It'll do, if the brake is pressed, it'll do by throttle adjustment or brake adjustment. That was an airbag problem. Here is the braking problem. And there you have to add all the timing constraints that are there. Similarly, the timing constraints in the logical specification will have to be added in every refined version. And when you go from one refined version to another, in the timing. So now you have to do a check between functional and timing. There is a check between functional and timing, and there is a timing check at the refinement level. So that is another mathematical problem, which is called valid region checking. I just want to share with you some names so that you can understand the gamut of the problem that we are addressing. And end to end, this sort of timing latency of a cyber physical system from sensors to actuators has to be formally verified. So you use these timed temporal logics and you use these timed algorithms to verify them. I'm just giving you information because we don't have the bandwidth to discuss all of this in this one class. If we get more time later on, I can take a special class to explain that. Finally, the state machines that we have done are only discrete machines. But as you have seen in your previous classes, that the state machine, while the temporal logic can be used to describe behavior of a dynamical system, but pure finite state machines may not be sufficient. So that is when you have to use what are called hybrid state machines. And this is just one small example of a atomic reactor cooling plant which has got rods, two cooling rods which go inside and outside and cool the system. I will share these slides with you, but let me just show you how the behavior is modeled. So this is the state machine. The state machine now has got dynamical equations in every state. So this X is the temperature. And it says that when there are no rods, then the temperature reduces and time step also increases. When the rod 1 is inside, then this is the rate of temperature change. When the second rod is inside, this is the rate of temperature change. And you want one of the two rods inside. These are the conditions under which the rods enter, and these are the values or conditions and assignments under which the rods exit. So it says that you enter into the system and your initial times are this and your initial temperature is this. Then if your temperature exceeds 550 and the total time that rod 1 has been outside, C1 is the time when rod 1 is outside, has exceeded 20 units, then rod 1 can be put in. And as the rod 1 is put in, you will notice that the temperature starts going down. Once the temperature goes below 510, then it goes back, it goes up. So the rod 1 is moved out. And the time for rod 1 is set to be 0. Similarly, if the temperature exceeds 550, then you have the option of putting rod 2 in, and again rod 2 goes back. So you can remove the rod or adjust the rods. Now you have a more complex state machine, which is called a hybrid automata, which means that the behavior can be modeled in a more complex manner. And as we go on to these levels of complexity, it becomes virtually impossible to accurately measure all dimensions of the problem. And that is when learning integration and ML come into the picture. So the controller, using the data that is generated from the plant, the controller is now converted using various kinds of deep learning, both supervised and RL based deep learning methods, convert even such complex hybrid controllers into these deep learned neural networks, which could either substitute the controller or it could be a corrector of the controller. Those are beyond the scope of this validation, but this is the architecture. And there are some very interesting things. For example, today many of these power schedulers. I mentioned in my original lecture about a power appliance scheduler. Which appliance will you schedule at your home automatically? And you want to optimize millions of things. My user comfort, my peak power, my timing. I don't want the oven to suddenly heat the food 5 hours before I eat. But if I have to do it at the same time that I eat, then I may have to reschedule my washing machine. And my washing machine must be rescheduled such that my clothes are dry enough for me to wear them after I eat. So how do I manage this complex mechanism while reducing my power, my air conditioner, and all these things? There we come to these deep learning algorithms. And these deep learning algorithms again require verification. And that is another story altogether about how to verify and validate the deep learning algorithms. With this, we come to the end of the validation part. As a summary, for validation, we had temporal logic, both untimed and timed. We had state machines, which could be FSMs or hybrid. And these could come from code also, from the code that is developed for the controllers. Complex C code and other code is developed. And then in addition to this, you will have ML based models. And we have seen some of the verification, self-verification or consistency realizability. Then we see intent verification, which is between layers of the same category. And then we see implementation verification. And then we see learn model validation. These are all extremely important research topics of today. And if you are interested, we can discuss this further. With this, I will complete today. If you have any questions, thank you for opportunity to discuss this nice topic. Any questions? Was this topic interesting?
Yes, sir.
Yes.
Yes, sir.
So please go through the recordings of these 3 lectures, and I will upload this slide also today. We can stop the recording. I think we are done. Those who have a class can leave. Anybody else, any other question, I'll be happy to answer.